LangGraph state management system employs a hierarchical graph composition pattern, where subgraphs serve as encapsulated nodes within parent graphs, sharing state through a common schema. This modular architecture enables the construction of complex workflows while maintaining clean separation of concerns between components. We are about to examine how checkpointing is implemented in this system, specifically through the MemorySaver utility, which provides in-memory persistence for graph execution state. The code demonstrates the creation of a subgraph that modifies shared state, its compilation into a reusable component, and its integration as a node within a parent graph, all while configuring state persistence at the parent level.
From LangGraph, graph import start state graph. From LangGraph, checkpoint, memory import MemorySaver. From typing extensions, import type dict. Class state type dict. Foo, str. Hash subgraph. Def subgraph node 1 state. State. Return foo, state foo plus bar. Subgraph builder equals state graph state. Subgraph builder, add node subgraph node 1. Subgraph builder, add edge start. Subgraph node 1. Subgraph equals subgraph builder, compile. Hash parent graph. Builder equals state graph state. Builder add node node, subgraph. Builder at edge start, node 1. Checkpointer equals MemorySaver. Graph equals builder. Compile checkpointer equals checkpointer.
This code demonstrates how to implement checkpointing and persistence in LangGraph using MemorySaver. The pattern shows a parent graph containing a subgraph as a node, where both share the same state schema through the foo key. The key mechanism is the MemorySaver checkpointer, which is passed only to the parent graph during compilation. LangGraph automatically propagates this checkpointer to all subgraphs, enabling state persistence across the entire graph hierarchy without manual configuration. The approach simplifies state management in complex workflows by centralizing checkpoint configuration at the parent level. This is particularly valuable in multi-agent systems where you want shared state persistence across agents while maintaining clean separation of concerns. The trade-off is that all subgraphs inherit the same checkpointing mechanism, which may not be ideal if different subgraphs require different persistence strategies. For such cases, the code hints at an alternative where subgraphs can be compiled with their own checkpointer equals true, though this isn't shown in the current implementation. The design choice to propagate checkpointers automatically reduces boilerplate while maintaining flexibility. In production scenarios, this pattern enables resilient workflows where execution state survives process restarts, though developers should consider memory constraints when using MemorySaver for large or long-running graphs. The shared state schema between parent and subgraph also means careful coordination is needed to avoid key collisions in more complex systems. Let's break it down.
From LangGraph, graph import start state graph.
Import start and state graph from the LangGraph graph module. Start is a constant representing the entry point of a graph, while state graph is a class for defining stateful workflows with nodes and edges.
From LangGraph, checkpoint, memory import MemorySaver.
Imports the MemorySaver class from LangGraph's checkpoint memory module, providing functionality to persist and restore execution state in memory.
From typing extensions, import type dict.
Imports typed dict from typing extensions for creating dictionary types with static type checking.
Class state type dict.
Defines a state class that inherits from typed dict, indicating it will be a dictionary-like structure with type annotations for its keys. This establishes a type-safe state container where each key's value type can be explicitly declared, though the specific fields aren't shown in this segment.
Def subgraph node 1 state. State. Return foo. State foo plus bar.
defines a function named subgraph node1 that takes a state object as input. The function accesses the value associated with the key, foo, in the state dictionary, appends the string, bar, to it, and returns a new dictionary with the updated value under the same key. This operation effectively transforms the state by modifying the foo field while preserving all other state properties.
Subgraph builder equals state graph state.
Creates a state graph instance named Subgraph Builder using the state class as its state management system. This initializes a graph structure that will manage state transitions, with state defining the data model for the graph's nodes.
Subgraph builder. Add node subgraph node 1.
Adds subgraph node 1 to the subgraph being constructed by Subgraph Builder. This single line registers the node within the builder's internal structure, making it part of the subgraph's node collection. No additional configuration or edge creation is performed here, just the straightforward addition of the node to the builder's working graph.
Subgraph builder. Add edge start. Subgraph node 1.
Adds a directed edge from the start node to the node named Subgraph Node 1 in the subgraph being constructed by the builder. This establishes a connection where execution can flow from the entry point to the specified node.
Subgraph equals subgraph builder. Compile.
Calls the compile method on the subgraph builder object, which processes the subgraph configuration and returns a compiled subgraph instance ready for execution. The result is assigned to the variable subgraph.
Builder equals state graph state.
Creates a state graph instance using the state class as its state management type. This initializes a graph structure where nodes will process and transform state data of type state.
Builder add node subgraph.
Adds a node named Node 1 to the graph builder, where the node is implemented by the provided subgraph. This incorporates the subgraph's functionality as a single node in the larger graph structure.
Builder at edge start, node 1.
Adds a directed edge from the start node to node 1 in the graph being constructed by the builder. This establishes that node 1 is the first node to execute when the graph begins processing.
Checkpointer equals MemorySaver.
Creates a checkpointer instance of the MemorySaver class. This object will handle checkpointing operations, storing state in memory rather than to disk.
Graph equals builder. Compile checkpointer equals checkpointer.
Compiles the graph using the builder's compile method, passing the checkpointer as a parameter to enable state persistence. This operation transforms the graph definition into an executable workflow with checkpointing capabilities. LangGraph's hierarchical composition shines here through subgraphs acting as encapsulated nodes within parent graphs, all sharing state via a common schema. The pattern demonstrates clean separation of concerns while maintaining state continuity. The subgraph modifies the shared foo field, and the parent graph orchestrates execution flow. Checkpointing via MemorySaver becomes particularly elegant through automatic propagation. Configuring persistence at the parent level automatically extends to all subgraphs, eliminating manual setup while maintaining resilience. This centralized approach simplifies complex workflows, but does impose uniform persistence strategies across the hierarchy. The design choice prioritizes reduced boilerplate over granular control, making it ideal for systems where shared state persistence outweighs the need for subgraph-specific checkpointing strategies. The shared state schema ensures type safety while requiring careful key coordination in larger systems to prevent collisions.
The subgraph builds its path, while the checkpointer whispers secrets to memory, leaving only echoes of forgotten steps.